Hi students. So today we start optimization tutorial 5b. Today I'm going to look at the test function again and we are going to figure out if this test function actually has a minimum point. Now remember in tutorial 5 we actually found out the stationary point for this function, and in tutorial 5a we showed that the function is convex. So today we will check out the sufficient conditions for minimization. I am Dr. Ganguly. So just to recapitulate, remember the test function in its one-dimensional and two-dimensional forms was given as these two equations in red. So we had the equation, for example, fx is x1 square plus 2x2 square plus e to the power minus x1 minus x2. And you can go back in tutorial 3 and 4 and check out as to how the minimum of these functions could be obtained, how it could actually be proved that these minimums correspond to stationary points, and of course the stationary points correspond to minimum points. So today we are going to try to find out the sufficient conditions for minimum are satisfied by the general function, where we are going to expand this two-dimensional function to the n-dimensional space. Now if you want to review, you can check out lecture 1 to 5 for some of the basics in optimization, and of course make it a point to look at the optimization playlist where I'm putting the lectures as well as the tutorial on my YouTube channel. So again the function which we are looking at is fx is x1 square plus 2x2 square plus 3x3 square all the way to ixi square and then all the way to nxn square. So this is part of the function, and the second part is plus e to the power minus x1 minus x2 minus x3 all the way to minus xn. So essentially this is the function which we are going to use at many points in this particular course for checking out different numerical methods, for example the gradient based methods and so on. And today we are going to look at the sufficient conditions for the stationary point of this function being a minimum point. Now if you are interested in the stationary point, look at tutorial 5 for that, and look at tutorial 5a for proof of convexity of this function. So we start with this function here, and of course we know that if we want to show that this particular function has a stationary point which is a minimum point, we need to find out the Hessian of this particular function and check if it's positive definite or not. So what I'm going to do is I'm going to calculate the second derivative of this function. So let's take the derivative with respect to xi. So when I take that, what happens here is we get one term from this ixi square term here. So that term is going to be 2ixi, and then the second term is going to be a negative e to the power minus x1 minus x2 all the way to minus xn. Now do remember that when you are taking partial derivatives, what happens is only that variable, for example xi is considered a design variable here, the remaining variables, for example x1 x2 all the way to xj xn, are being treated as constant in that differentiation. Now this particular expression, I'm going to call this exponential function as a, and this function is going to be present in all the derivatives, so it's going to make it simpler to write this out. So I can write this df by dxi as 2ixi minus a. Now let's take one more derivative. So I take the second derivative of f with respect to xi, and so the 2ixi term simply becomes 2i, and the second term here, the exponential term, becomes plus e to the power minus x1 minus x2 all the way to minus xn. So remember, whenever we are differentiating this exponential term, it's throwing a negative 1 at me because I'm differentiating it with respect to one of the terms which are in this exponent sign. So that's what's happening here. When I differentiate it twice, I get two negative ones multiplied together, and so I end up with the plus here. So again, the second derivative simply becomes 2i plus a, where a is the exponential term here. Now one thing you can immediately see with this value a, that it's always going to be positive because the exponential function is always positive. So that we know whatever is the value of x1 x2 or xn, that is whatever be the point at which the design variable is stationary, the value of a is always going to be positive. So now let's take the cross derivative term, which is d2f by dxi dxj. So I have to take this derivative here, df by dxi, and we have to differentiate it with respect to xj. So to do that, of course, what will happen is the first part 2i xi, that's simply going to give me 0 because there is no xj in this particular term here. But in the second term, I'm going to get e to the power minus x1 all the way to minus xn, because a negative 1 is going to get thrown out when I differentiate it from the minus xj term which is present in the exponent here. So again, I'm simply going to get simply a as the cross derivative term d2f by dxi dxj. So now we have these terms here. So especially if we look at the second derivative terms here, d2f by dxi square and d2f by dxi dxj, they are going to let me form the Hessian matrix. Remember that a is always greater than 0 in this case. So from these two differentiation terms, I can write the Hessian matrix in this manner. So you see here that as far as the diagonal terms are concerned, I can start with I is 1, that's going to give me 2 plus a. I is 2, that's going to give me 4 plus a. I is 3, that's going to give me 6 plus a. And when I is n, I'm going to get 2n plus a here. Now, as far as the off-diagonal terms are concerned, they are simply going to be a, which I can see from this particular second derivative. So all the off-diagonal terms are simply a. So now my problem is a mathematical problem. I need to prove that this Hessian is positive definite if I want to show that this function has a stationary point. So one of the methods to do that, especially because we have a general function here, we have dimension n, then what we can do is that we can use the method of leading principal minors. So in this method, what happens is that if we show all the leading principal minors are greater than 0, then we can say that this Hessian matrix is a positive definite matrix. So the first principal minor, which is a leading principal minor, is this term 2 plus a. So again, I take the determinant of 2 plus a, which is simply 2 plus a, and this is of course greater than 0 because a is greater than 0. Now I look at the second principal minor, which is the leading principal minor. So I get 2 plus a, 4 plus a. That's this determinant here. Now I can expand this determinant out and I get 8 plus 6a. Again, this is greater than 0. Now I take the third leading principal minor, which is this determinant here, and again I get 48 plus 44a, which is greater than 0. So I can continue in this manner, and at least if I look at it from an empirical perspective, I can see that this particular theory of the leading principal minors being positive, that's being satisfied at least up to now. So let's try with n is 4, and then again what happens that I get 400a plus 384, and this is greater than 0. So all these leading principal minors are positive here. Now how am I getting these very quickly? Now at least till the 2 by 2 system I was doing this by hand, but beyond this, because I'm somewhat lazy in this matter, I used the online system known as Simbo Lab. So you can also check this out. This is a very useful system if you are checking out different things in math. And so for example, for n is 5, I can put in the matrix here and I can get the determinant and I get the solution right here. Now all these of course look positive because a is positive, and certainly that would make this quantity a positive value. So let us summarize till now what we have learned. We were trying to figure out if this particular determinant is greater than 0, and we checked out the cases of n is 1 to 5, and all these of course satisfied the cases of the determinant being greater than 0. But I would like to actually find a general term here, that is, given any value n, I should be able to get the value of d. Now if I look at it, I can see certain patterns here. So I can certainly say that the value of the determinant would be some constant term, so that I am calling t1n. It's simply a function of n here, and a second term which is actually multiplied by a. So that's the general form which I am getting here. I also see some commonalities of things which are happening here, and I spent a lot of time staring at this particular set of 5 equations to figure out if I can get any general term. Now, of course, if you are a faculty or a professor, you can use this kind of problem as a test problem to see if a student can get it. It's a hard problem, but maybe there are some precocious, intelligent students who may be able to get that. So after studying a lot, I figured out the general term here. And the general term actually has this form that the determinant is T1n plus a T2n, and the T1n is 2n, T1n minus 1, and T2n is 2n, T2n minus 1 plus T1n minus 1. So these are relationships which I can use, and let's check this out and see. So let's check it out with n is 1. N is 1, of course, is the point at which all things start. So n is 1, we know d is 2 plus a. So we see t1 1 is 2 and t2 1 is 1. So all I have done is I have replaced n by 1, and so I get these two. Of course, this simply starts off the algorithm here. Now, if it's true or not will become clearer if we try things with n is 2, for example. So when I put n is 2, I of course have from my hand calculation that d is 8 plus 6a. So here what would happen is that the T12 would be obtained in this manner here. So what I get from this formula T1n is that I am getting T12 is 2 into 2 into T1n, that is T11, and then I get here this is 4 into 2 is 8. So all I have done is that in these equations I have substituted n is 2, and that has given me these values, and I have taken the T11 from this equation in purple, and I have taken the T21 from again this equation in purple, which were coming from the previous value of n here. So this relationship gives me T1 2 is 8 and T2 2 is 6, which is something which I can see in this determinant as 8 plus 6a. Now let us try to do this for n is 4 here. So I have tried to do it for n is 4, and n is 3. I know d is this value, so I can see that T13 would be 48 and T23 would be 44. So these are the coefficients of the constant term and the coefficient of a. Now, once I have these two, I can use these two relations in green. So I write these two out here. I put n is 4 and I get these equations here. Now you can see T13 is 48. So I put that here. T23 is 44. So I put that here. And I put T13 is 48 again. And then after some simplification, I get 384 and I get 400 here. So that does satisfy this particular equation in pink which I have obtained before, that is d is 384 plus 400a. Now of course we also had obtained n is 5, d is 3840 plus 4384a. So what I did here is I took that value n is 5, this d value, and so I know T15 and T25 here are the coefficients of the constant term and the coefficient of a, and then I tried to figure out what would be n is 6. So here I am trying to predict the value, and so T16 would be this value here. Again I go to this equation in green, the first equation, and I substitute n is 6 here, so it relates this to the condition n minus 1, which is T15, and so I get this value here 46080. Similarly T26 from the second equation here becomes this equation, and then I simplify it and I get 56448. So the determinant for the case n is 6 is going to be this value. Now of course you can see that this value is also always going to be positive because a is positive. So I can check this. So I went to Symbolab and I checked it out and I got exactly the same determinant from Symbolab also. So now I have found the general relation which I can use to predict this determinant, and I no longer need to bother about calculating this determinant anymore. Now what has this helped me do? This has helped me figure out that for this particular function f of x, which is given in red, I have the value of the principal, leading, minors, and so that is given by this value of d here. And looking at this value, I know that since a is 0, this particular value is always going to be greater than 0. So also you can see that T1n is greater than 0 and T2n is greater than 0, because I started out with values T1 and T2 at 1, which were greater than 0, and then it goes on. Now remember here, of course, n is being used only at 2 and beyond, so that's something to keep in mind. So essentially we have figured out that all the leading principal minors are positive, and this is a condition which shows that we have a positive definite Hessian matrix. Now if you are somebody who has some doubts about this, you can go to Google and check out. There are many pieces of information out there where this particular thing is proved. So this is something you can see in many situations. In the previous tutorial 5a, I had also shown that this particular function is a convex function, and we had broken this function into two parts, and we had shown that each of these parts is convex, and therefore this is a convex function. Now of course in today's lecture, since we have shown that the Hessian matrix is positive definite, this also is a secondary proof of convexity. And today this proof also tells us that this point corresponds to a minimum point. Remember, that is the sufficient condition for a minimum point. So for that we can of course say that the local minimum, if we obtain this for this particular problem which we have in tutorial 5 for example, that is also a global minimum. So these are certain things which now we have seen here. So the function is very well behaved. It's a nice function and it is amenable to mathematical calculations, and therefore we are going to use it at several places in this course in the future. So today's lecture, you figured out the test function in detail. Now make sure that you look at all the videos in tutorial 5, that is tutorial 5, tutorial 5a, tutorial 5b. I actually ended up making 3 videos because it took me some time to get this function in complete control. And so the first video, tutorial 5, is about the stationary point. Tutorial 5a, that's about the convexity of the function, and tutorial 5b essentially lets us get the sufficient condition for the minimum satisfied. Tutorial 5b took me some time because there was some complexity in figuring out the particular general term for the determinant, and this problem of course may be interesting in many situations, so you can look at it and you can of course use it at different places. If you have any comment on this particular function or this video, please leave it in the comment section because I'd like to figure out if there are any alternative ways of doing this problem in some simple manner. So maybe there is some simpler way to prove that the Hessian of this function is positive definite. So that's somewhere mathematics people, mathematicians can probably help me here. Of course, remember, optimization playlist contains the full course, and do check out the different videos in the optimization playlist. Now in the next video lectures on, or rather I should say tutorial, we are going to start looking at the direct method. So most of the optimization problems actually require numerical methods to solve them. They are not amenable to methods such as the KKT conditions and such as the necessary and sufficient conditions based only on calculus. So we are going to start looking at these numerical methods, starting with some basic concepts such as how to split the problem into search direction and line search. See you soon.